So before we just start, just to give a little insight into what we plan for this talk to be. So this talk is more of a quick intro to try and ease the nerves of anyone that's wanting to go into AI, but they think, oh, I'm not smart enough, or I don't know the math behind it, or blah, blah, blah. This is kind of just to show you that you don't really need to know every single thing about an artificial intelligence neural network in order to actually start working with it. So we can go on to the next slide. And Graeme will introduce us.
Okay. First of all, just the basic structure of the neural network. So the neural network is a network of connected nodes. So there's multiple layers, and each layer would have multiple nodes, and these nodes are then connected to other nodes in other layers. So just to give you a basic idea, if I have, let's say, 10 nodes in the first layer, this first node on the first layer was connected to every other node in the following layer. Anyways, so what happens is we have input data that is sent into these nodes, and there's weights that connect these layers. And as data is sent through one node to the other, these values are multiplied as they travel along. And basically, this just helps us get a bigger value as we move on and on. Eventually, we'll be multiplying these values with what we call activation functions. If this value, after it's been multiplied with the activation function, is higher than a certain threshold, this node will be activated and will be used further on down the neural network. If it isn't, it just won't be used. It won't be fired. So what happens is we start at the input layer, data is sent through, gets passed on through multiple layers of nodes. If it reaches the output layer, which is the final layer, it can give us an estimated value. So we can get multiple outputs technically, but we take the highest output, and the highest output will be our prediction. So our output, every node in our output layer would represent a category, and what our neural net tries to do is predict the category, and the highest prediction would be associated with the category, and that would be our final prediction. So simply put, we're just trying to model how the human brain works.
Yeah, just to jump in there, for everyone watching, this is going to be very complicated, and you're going to think, but I thought you said this was simple. So this is all just the theory behind it that we're just laying it down. We're gonna simplify it now. But the basic idea behind this is modeled on neurons in your brain that fire in a certain order, and they're connected by synapses. So, or synapses, don't ask me the pronunciation. So the idea behind it is if we connect things properly and they're firing in the right way, then we should be modeling how the human brain is detecting patterns and matching things. So in the next slide, we'll just show an example of a very basic neural network. So we have our input layer, 3 inputs here, and every single neuron, as we talked, we call these circles neurons, by the way. Every single neuron is attached to every single other neuron in the next layer. As you can see, there's a whole bunch of lines there. And the idea behind this is that as we train this neural network, only certain neurons are going to fire for given inputs. So it's training itself to learn patterns in the data so that it can actually identify things. Here we only have one output, but you can have more than one. It depends on the problem. So as Graeme mentioned before, if we're, say, trying to classify something as a cat or a dog, then we would have 2 outputs, one for cat, one for dog. If we're, say, trying to estimate a value, like the price of a house given its area, the mortgage, etc., then we would have one output because we're trying to predict a single value, the price. I hope that everyone's following so far. So if we go to the next slide, we should see just how the data works. So in the example we're going to show you later, we're actually detecting numbers, predicting numbers based on a given image, telling us what the number is. So the 784 there is to display that there's 784 pixels in the image, and we're feeding in every single pixel color value. It's not RGB, so it's just, how saturated that pixel is, basically. All 784 get fed into the neural network, and the neurons will fire. And you see here, our numbers are from 0 to 9, so we'll have 10 different outputs, one for each of the numbers it could possibly be. I don't know if Graeme would like to elaborate further on how this works.
No, you pretty much got it nailed. We just, you'll see it's a 28 by 28 picture. It gets scaled down into a 1D array, which I'll show you later. It gets passed through each layer, and if you see that it shows a 9, it received a 0.5 value, which is probably the highest, which is why the color there is going darker and lighter, because the higher the value is, the more likely it is that number. So that 0.97 is just the final output, and 0.97 is in a specific range. 9 happened to be in that range, and that is why it's a 97% chance at the end that it is that value. So we'll just continue on. Anything else from you?
Yeah, I think we can just continue. So the next slide should give more insight into how this is actually working. Because it's quite weird. Some people would think, but then how is this actually predicting things? How is this actually giving us the right output? So what we haven't mentioned is that each of those little edges, all of those lines have a weighting to them, a number, usually between 0 and 1. And what happens is the value in the neurons, the circles, gets multiplied by the weight that it travels along. And so what happens is every neuron in the next layer will be summed up. All of the previous edges connecting to it get summed up and added together and then fed through some function. And then that is that neuron's output to the next layer. And so what happens is we're going to be feeding in inputs. They get multiplied, they get added, they get sent through. And what happens is at the end, we're going to have values in those output layers. And now we're going to do a process called supervised learning. So in supervised learning, that just means we're going to give an image and we already know what that image should be. So you can see here, the input is a 7. We know in our data that that input is a 7. So we're going to feed it through and we're going to see what the neural network thinks it is. And if the neural network thinks it's a 2 or something like that, we're going to be updating all of the edges in this whole network to try and align it more to become a 7. So we're going to be calculating basically the error of the output and seeing how we should shift everything based on this error. So that technique of training these weights is a big word. We call it back propagation. And there's a whole bunch of math behind it. Don't concern yourself with it. Just know that the outputs will be tested against what we think the output should be, and then all of the weights get shifted so that we're closer and closer each time to the expected outcome. So, Graeme, I don't know if you want to go to the next slide and show back propagation.
Yeah, so this is just an example of how the back propagation works. Is the data gets in through, we can see that it predicted a 5, we know it's a 5, and it'll just update all the weights going backwards through all the nodes that were, through all the neurons that were fired, they were activated, and it'll, yeah, like Ethan said, try and align it more towards 5. So that's just how we call the forward way, this forward propagation, where it tries to predict, and back propagation is where it tries to update the weights in order to correctly identify the next time, more correctly. And yeah, so that's just pretty much how the training works.
So it should also be noted that we usually don't do this after every single prediction. Otherwise, what we'll end up doing is we'll keep jarring our network one way or the other, because we'll give it a 5. We'll say, okay, this was supposed to be a 5. So it'll shift to go closer to 5. Then next we give it maybe a 9, and it'll shift closer to go to 9. So that way, logically, if you think about it logically, then we're just telling this thing different things every time and contradicting, and it's not going to train well. So usually what we do is we'll do like 100 different predictions, and then we'll sum up the error for every single one of those, and then we average it out, and then we do the average change so that we're actually training it to be generalized. Because otherwise, we could train this thing to predict 0 perfectly every time, but then it will never predict 1 to all the rest of the numbers. So yeah, we call that batch learning. We learn in batches.
Okay. Going to move on to the next slide. Yeah, as you mentioned, we're doing supervised learning. We're doing image classification. And then why should we care? Currently, many companies are implementing neural networks as part of machine learning in their organizations. It is becoming a norm. It isn't just a trend. It's becoming a norm. It's becoming more and more adopted as the days go by.
Yeah, as Lucky mentioned, like AI is becoming very prominent. It's no longer just a trend or some buzzword. Many companies are using it, and there's considerable revenue growth from actually implementing machine learning in your business. So, just to give examples of where it's actually good to use is pretty much any automated task where it's not a simple switch or an if statement of, oh, if this, do this, where there's considerable factors involved where, you would think that a human needs to be there to actually manually go through this process. But if you could automate it, this is where machine learning comes in. You would train the AI to be able to determine the correct route to go depending on all of the different input data. So for these inputs we're doing now, it's the pixel values because we're doing image classification. But you could put any simple input as long as you can quantify it in a number. So for instance, like we're talking about the price of the house. Like you could put in like the size of the house in square meters, the area in coordinates, any numerical data, and it will learn all of these inputs and predict properly. So the whole idea is that we're actually teaching this program to think. We're not just forcing it to do certain things based on certain inputs, because then that would just be simplified with a simple switch or an if statement. And that's not what we want. We want something that can think, or at least seem to think.
Okay. So what I'm going to do now is just show a basic example of a neural network that we made. So just to show you the data that we're using, this is what it looks like. It's called MNIST, which is the data set. It's 70,000 handwritten pictures, all 28 by 28 of just different numbers. And what we're going to do is pass these into the model. So let me just find the view. Yeah. So first of all, we load the data into the different variables. So we've got the train and test data. So what we do with the trained data, which will consist of the first portion of the data, it's around 60,000 images, is with the training, we only send the training data into the model. Once that is done, once the model is trained, we send in the remaining data, which is the test data. It's another 10,000 samples. We send that in after the model's been trained so that we can test the model on unseen data. So that's just what that is. So then what we do...
Sorry, just to cut in, just to note, we are using the Keras Python library here. And this is where you'll see that it's very simple, like to train your own AI neural network in like 10 lines of code.
Yes. Okay, so after we've loaded in the data, we have to, there's a function that's called shape. All that does is it converts all the images into a 1D array. So instead of 28 by 28, it'll just become 1D and behind 784, an array of 784 pixel values long. And currently the images are stored with value that represents the RGB value. So in order to get it into a value we can work with, we need it to be between 0 and 1. So what we do is we divide it by 255 just to get it into that, because the RGB value is 255. So that once we're done with that, we've pretty much set up our images. What we do after that is set up the model itself. So we set up the input layer, which is 28 by 28, which it will convert into 784. We set up one hidden layer, which is 128 neurons big, and we give it an activation function. We mentioned the function earlier, and what this does is once a weight is passed on to the next layer, it goes through this function here to determine whether it should keep going. So if once it's been multiplied with this activation function, if it reaches a threshold, it'll continue. But yeah, that's just, it's called ReLU. That's just that activation function's name. And then we have our output layer, which also gets an activation function. And because we had 10 output categories, it's a size of 10. So then we set up, or we just compile the model, we just give it an optimizer, the method we want to use to calculate loss, and then the metric we want to obviously calculate the accuracy over time. And what we do then is we actually train the model. So we give it 10 epochs. Epochs is just the number of iterations. So we want to pass through those 60,000 images multiple times. So one epoch will send all 60,000 images through, and they'll be passed through 10 times in order to train it. And then we just give it the train data. And so then what I do here is I just print out the loss. Once the model's been trained, we send through all the test data, and then we just print out the accuracy on the test data. So this will just give us an idea of what it looks like on data the neural network has never seen. And then lastly, I'll just grab a random image from the data set and just show you what it looks like. So I'm just gonna run this and we'll see what happens. So yeah, so it's going through all the epochs and it's currently training. If you see here on the left, it shows a number out of 1,875, and that just represents the batch number. So this is separated into batch sizes of 32 images, which is what we spoke about earlier. So as you can see, we started off with an accuracy of 92%. I think that was just the final one after the last batch. I think it started quite low. But we ended up with a final accuracy over here with 99.5%. That's on the trained data. After that, we did the test data, and on data that it's never seen, it managed to get 97.7%. And then I pulled just the first image from the data set, and it predicted that it was a 7. So if I just show the image that it grabbed, yes, it is a 7. So I can pretty much do that with any image out of the train set, and it'll try and predict that number. And that's pretty much how that works.
Awesome.
Yeah, so essentially, like, it's a very simple process. As you saw there weren't many lines of code. From my experience, the hardest part to actually training these AI is finding the data, finding enough data, finding enough like quality data, not data that's actually spread out across different examples with some outliers even, and formatting that data properly. That's honestly the hardest part to training these models. And now once this model is actually done, this prediction's done, you can wrap this up, throw it on a server, and then just feed it images of numbers, and ask it what it thinks that number is, and then use that prediction. So you can see in these 10 lines, we've trained a classifier to look at images of numbers and tell us what that number is. And so in these few lines, we've trained something really strong that you couldn't do with a normal if statement or normal programming, basically.